Welcome, this is the law of motion kinetics, and here we're going to cover friction part 2. Here we're just going to go over some example problems. If you need an explanation on why these are true, you have to watch part 1 where I go over the theory as well as the equation. So here, example 1. A 5.0 kilogram box is pulled at a constant velocity by a 10 Newton force along a rough surface. Determine the coefficient of friction. You're solving for mu. Please understand it is being pulled by a constant velocity. So the mu that you're solving for is going to be mu k because the object is moving, kinetic friction. So start this by looking at the x and the y axes. So in the x direction, we say it has a constant velocity. So F, the summation of the force in the x direction equals to 0. Then we saw that it is also 0 in the y direction. The object is not floating up or down. Now we look at the diagram. The free body diagram, all the forces are balanced because the object's at a constant velocity. The force going up is normal. The force going down is force of gravity. The force going to the right is the pulling force. You could call that F or T. And the force that opposes it is force of friction. Again, here I just write the F. I do not write the subscript. You don't have to write F of like K here or F of S. Okay, you just know it's force of friction, right? There's no alternate diagram because this is just in the traditional XY coordinate, right? So if we do the summation of the forces in the x direction, because we're going to solve for the static, the mu, we saw that the object is equal to 0 because it's at rest. So we do 0 equals to F minus mu n. We have to solve for n though. That's the normal force. So the normal force is now needed. And this means we have to solve it for it in the y direction. So summation of my forces in the y direction equals to n minus fg. That is equal to 0 because it is stationary. Add mg to both sides. You get n is equal to mg. Now you can substitute the normal force and continue working in the x direction. Here you're going to add, here you can do I could show you the algebra, right? I can do the algebra here on the side, right? So 0 equals to mu, sorry, give me a second. 0 equals to F minus mu mg. So add mu mg to both sides. You get mu mg equals to F. Then divide by mg. So you get mu is equal to F divided by mg. That's how they got here. Okay? That's just the algebra if you care. Right? Plug it in. You get your answer. Mu is equal to 0.204. So this is higher than ice. Oh, but this is moving. So it's probably like a plastic surface, maybe? A wax surface? Okay. Let's look at the next example. Okay. Here, determine the acceleration now of a mass being placed on a rough 30 degree incline. Mu s equals to 0.2, mu k equals to 0.10. We have to look at it and see where the motions are. So we would say that in the x direction, which is parallel to the incline, the object is accelerating. So we said the summation of the forces in the x direction equals to ma. In the perpendicular direction, the y, we say it's stationary. It's not floating up in the air or going into the ground. So we say summation in the y equals to 0. The free body diagram looks like that. And again, I broke this down into its horizontal and vertical component, right? Remember? Okay. This is F cosine theta, and then this is F. Hold on, is that right? Yeah, sine theta. Okay. Right. Then you can now solve. Okay. Summation of the forces is Fg sine theta minus mu k. right? Because the only thing left is the FG sine theta. This is the part of gravity that is pulling it down. Opposing it is the force of friction. Substitute because this equals to ma, okay, because the object is moving in the x direction. Okay. Then the m is but we can't do this because we need to solve for n. Okay, so we have to go back and look at the y part to solve for n. Okay, so summation of the y forces in the y equals to n minus fg cosine theta, and that equals to 0 because again we said it right here. The summation in my y direction equals to 0. So that is the reason why it is set equal to 0 right here. Add mg to both sides. Okay, you get n is equal to mg cosine theta. You plug it in here. Notice that the masses cancel out. So a is equal to, in short, if you can write it, a is equal to g sine theta minus mu k g cosine theta. And that's the answer there. Here's some conceptual checks for you to understand this. Again, this is something you shouldn't memorize, but make sure you can derive and analyze. The acceleration for a block sliding down a rough surface can be the acceleration is equal to g sine theta minus mu k g cosine theta. So the question is this: where did the mass go? The mass cancels out. When an object slides down the ramp, the acceleration doesn't depend on the mass. What are the two forces at the end that affects the acceleration? Well, you have this, the g cosine theta. This is the gravity part, and this is the horizontal part of the gravity that's pushing it. Then opposing it, it is the force of friction that is opposing it. Okay. What happens as theta approaches 0? That means the degree of this ramp becomes completely flat. Well, if it's flat, there's no more horizontal part of gravity. So the g sine theta becomes 0 because sine of 0 degrees, right, is equal to 0. Okay? So it becomes no more because it's completely flat. The friction force, cosine of 0 becomes 1. So it just becomes mu g. Okay? Which is, this makes sense because now it's just the horizontal part of gravity. No, the horizontal part of friction. Here's the third case that you would see. This is a box on a surface, but now you're pulling it at an angle. This is a 5.0 kilogram box is pulled on a rough surface. Mu k is equal to 0.10 by normal force at 37 degrees. Determine the acceleration. Again, I asked you for the acceleration, but you understand you have to calculate for the normal force too, right? So we assist this by looking at the directions first, right? Is it moving in the x direction? Yes. The object is accelerating in the x direction. So summation of the forces in the x direction equals to ma. In the y direction, it is stationary. So we say summation of f in the y direction equals to 0. The free body diagram looks exactly like this. Once we broke the f into its component form, let's do that here. This is going to be here theta. So the horizontal part is going to be f. X is going to be equal to adjacent. So that is f adjacent cosine theta. And then I had to think about my trig for a second there. And then you have blue for the vertical part. And this is Fy is equal to F sine theta. All right. Again, this is the component part. So that's part of the alternate design. Okay. Summation of the forces in the x direction. We only see force of friction right here. Force of friction. Let me change my pen color. So in the x direction, you see force of friction and f of x. Okay, that's where you have here. F of x is going forward, force of friction is going back. That's why it's minus force of friction kinetic. We saw that this is moving in the x direction, so we set this equal to ma because again the object is moving. But again, you see that n that does appear. Okay, so we have to solve for it. So again, you have to look at the y part to solve for normal force. Okay, plug in 0 there because again the object is not moving in the y direction. Okay, that's why the 0 is here. Do you see? 0, 0. Okay, do some algebra. Do you really need me to show you the algebra? Add mg to both sides. Then you need to get rid of the f sine theta, so it's minus sine theta. Okay, so it should look something like that. Okay, n is equal to mg minus f sine theta. Okay, plug it back in. You will see this. You have to divide m over to both sides. I've seen this equation on the AP exam. You should not memorize it, but understand where it comes from and be able to analyze it. Okay, plug in the numbers, you get the answer. Just let you know the AP exam really doesn't care about an exact answer. If you know how to derive this equation and explain it, you're good. Now we're going to analyze this object being put on a rough surface. In this case, you will see that the force of the acceleration, the x-axis, can be thought about it like this. This is the pulling in the x direction. Then this is the friction force divided by the mass. Breaking it down into its math parts, it looks like that. So why does this one actually have mass? Why the other one doesn't? Mass didn't cancel out. This object isn't sliding down the ramp. What are the forces in the end? Well, you have an f cosine theta part here, which is the pulling part. Then you actually, do you see the negative mu k? If you distribute this over to this side, a negative k times a f sine theta will equal a positive number, mu k f sine theta. You see how this is positive, so it's actually helping. So the mu k sine theta is actually helping. It's increasing the acceleration, okay, of the object. The only thing that is hurting it, the only minus here, is the minus kmg, which is decreasing the acceleration. There's a last question. This is really complicated, but what happens when the angle becomes 90 degrees? Like you pull it straight up. What happens with it? Well, you know that the g cosine theta becomes 0 because cosine of 90 degree becomes 0. So there's no more horizontal part. Then the friction force becomes weird, right? Don't think about it because it technically disappears because the object is no longer on the surface. Okay, there you go. Those are your part 2 for friction, where we went over calculations.